Hello, viewers. In today's session, we are going to discuss another important functional equation, right? And here in this session, we are going to discuss this functional equation where we have f of xy is equal to xfy plus yf of x for all values of x and y belonging to the set of positive real numbers. And here an additional condition is also given, that is f of x is differentiable in this interval, that is from 0 to infinity, and we have to find out the function f of x. So here we'll solve this functional equation with the help of derivatives, right? So we'll use the method of partial differentiation to get the value of f of x. So we are given the functional equation, that is f of xy is equal to x f of y plus y f of x for xy greater than 0. And remember, here x and y are not equal to 0. Now we'll differentiate this functional equation both sides partially with respect to x. So differentiating partially both sides with respect to x, will get d by dx of f of xy, and here we have del of del x x fy, and here we have del of del x y f of x. Now here we have f prime of xy, and by chain rule we have to differentiate this product, that is xy. And here when we are differentiating partially with respect to x, then y is treated as constant. So we have simply f of y outside this operator, and we have del by del x of x, and here we can take y in front of this operator, and we have del of del x of f of x. So now here we have f prime of xy, and the derivative of this product xy with respect to x is simply y, because the derivative of x with respect to x is 1, and here this quantity is 1, so we have f of y, and here we have y times f prime of x. So this is our equation number 1. So now this equation 1 is going to be very important in getting the solution of this functional equation. So here what we will do, we'll replace y by x and x by 1, right? So replacing y by x and x by 1, let us see the changes in equation 1. So we have f prime. Now we are replacing x by 1. So here we have 1, and y by x, here we have x for y, and here also we have x, and here we have f of x, and here we have x, and here we have f prime of 1, right? So now we can also write this equation as x f prime of x, and here we have f of x plus x f prime of 1, and let us call this equation as equation number 2. So here we see that we have f prime of 1, that is the derivative of f of x at x is equal to 1. So let us take f prime of 1 as a. So now we can write equation 2 as x f prime of x, and here we have f of x, and here we have ax. For f prime of 1 we have written that is a. So we have now this equation. So now let us call this equation as equation number 3, right? Now let us consider the derivative of f of x over x, right? So we can take the derivative of f of x over x, and then we'll connect this derivative with this equation, right? So here, applying the quotient rule for the derivatives, we have x, then we have f prime of x, and then we have f of x, and the derivative of x is 1, and in the denominator we have x square. So here we have used this result, that is, if u and v are functions of x, then the derivative of this quotient is given by v du over dx minus u dv over dx divided by v square, right? So here, from this equation, we can now write dy dx of f of x over x is equal to x f prime of x minus f of x divided by x square, right? And multiplying this derivative with x square, we have x square d by dx of f of x over x, and taking this term to this side, we have f of x is equal to x f prime of x, right? So now, substituting this value of x f prime of x in equation number 3. So now equation 3 gives us, for x f prime of x, we can write this expression. So we have x square d by dx of f of x over x, and here we have f of x, and here the right hand side is f of x plus ax, where a is f prime of 1. So now we can cancel out these two terms. So we are left with x square d by dx of f of x over x, and here we have ax, right? Now see here, this x and this x get cancelled, because we have already assumed that x and y are not equal to 0. So we can cancel this x with this one. So we are now left with x dy dx of f of x over x is equal to a. Now taking this x to the denominator of a, we have dy dx of f of x over x is equal to a over x. Now integrating both sides with respect to x, right? So here we have dx, and here we have c as the constant of integration. So now in the left hand side, the integral of d by dx of f of x over x is simply f of x over x, and here we have a integral dx over x plus c. So now we can write f of x over x is equal to a, and this is equal to the logarithm of x, and c is the constant of integration. So now let us multiply both sides by x. So we have f of x is equal to ax log of x plus cx, right? So this is our function f of x. So now let us find out the value of this constant of integration c by using some initial condition. So from the given functional equation, we can write, if we take x is equal to 1 and y is equal to 1 in this equation, then we have f of 1 times 1, then we have 1 f of 1, and then we have 1 f of 1. So this is simply f of 1, this is f of 1, and this is also f of 1. So from this equation, we have f of 1 is equal to 2 times f of 1, and solving this equation, we have 2 f of 1, minus f of 1 is equal to 0. So f of 1 is equal to 0, right? So this is an important condition, that is the value of the function at x is equal to 1 is 0. So we'll use this condition to find out the value of the constant of integration. So now taking x is equal to 1 and f of 1 is equal to 0, in this equation we have f of 1, then we have a1, and this is log of 1, and here we have c times 1, right? Now f of 1 is 0, and here we have a, and log of 1 is 0, and here we have c, so this is simply c. So the value of the constant of integration c is 0. Now let us substitute this value of c in this equation. So we have f of x is equal to ax log of x. So this is our required function. So we can also write this function f of x as f prime of 1, because a is f prime of 1, and here we have x log of x.